Welcome everyone to another Texas Instruments Australia webinar. In this session, we'll be looking at an introduction to discrete random variables. My name's Peter Fox. I'll be your host and indeed a panelist for this evening's webinar, and I'll be joined by Mr. Peter Flynn. Let's see if I can get Mr. Flynn on board. Are you there, Peter?
Yes, good evening, Peter and punters.
That's it. It's a little bit like something out of the Two Ronnies. We'll have to be careful we don't slip down that slope. So let's get started. Whenever I introduce a new topic, I try to do it through an appropriate application, event, game, or problem that students can explore. This one, which is actually from the Senior Curriculum Inspiration site, is titled Great Expectations. If you look at those dice on the side, they look a little bit different than our regular set of dice. In fact, in the game, the students have an option to play with three. They're virtual dice because I don't think too many people have dice that look like that. You can actually buy them. They're called grind dice, or you could make your own. They don't have to be those colours. But the idea is that students select a die, either red, green or yellow, and then they simply roll their die and their opponent rolls their die, just one opponent, and the highest number wins. So if Mr. Flynn was using the green dice, I might have the red dice, and you can see whenever he rolls a 4, he's going to beat my 3, but my 6 beats his 4 and indeed beats his 2. If Mr. Flynn rolls a 2, I'll beat him with anything that I roll. So it's an interesting dilemma as to which die is better, the green or the red. Then you can try the yellow versus the green, and then the yellow versus the red to see which one is the best. The results might surprise you. For those that are in the know, they're referred to as non-transitive dice, a little bit like rock, paper, scissors, and it's certainly quite alarming for students. As you sit there and ponder these numbers on the screen, if you calculated the expected value for the red, green or yellow dice, you'll find that they all have exactly the same expected value. So one of the good things about this, apart from just doing something a little bit unusual, is that it tells the students it's not always the expected value that's going to help us solve a problem. It seems to be the go-to for a lot of students, but it's important that they understand what is the expected value telling you about the probabilities. And there's a link down the bottom of the screen for the Senior Inspired Curriculum. Another activity is called Greedy Pig. Now, I'm guessing most students have experienced this game. I know my 2 children experienced it in year 7 and 8. I actually think it needs to be bumped up a little bit higher in the curriculum. The fact that all students stand up and students keep on going until such time as pretty much they're the last one standing. What tends to happen then is it negates any of the real probability learning that we can get or glean from this game. The other thing, it's often used as a lesson filler, just as a bit of fun, and therefore we're actually devaluing the huge amount of mathematics that we can get from this game. So this one is also on the Australian website, and it focuses on what is the best winning strategy for winning at Greedy Pig. And as you'll see there, what if you can't see what everyone else is doing? So in other words, you don't know if anyone is virtually standing or not. You don't know what their score is. So you're only left with the information that's on your screen about what your current score might be. Now, I've put that activity up onto my calculator just so you can see what the game looks like, and I'll spend a couple of minutes going through this one before we move on. So the instructions for Greedy Pig: if you roll a 2, your score is automatically set down to 0. So let's have a look at the first one, and we pick it up. It's a program that simulates it, and I'll just press enter, and it says roll number 1, you got a 6. Would you like to continue? Yes or no? I'll select yes. And it said roll number 2, you scored another 6. Your total is now 12. Do you want to continue? Sure, why not? My total is now 13. I'm a bit of a gambler. I'll say yes. My result's now 17. I think I might sit on that one. And that's it. That's all that game does. So it's essentially simulating what students are doing in the class, but they can't see what everyone else is doing. On tab 2, that is problem number 2, they get to simulate a collection of games. So let's see how that varies a little bit. Piggy 2. So it says how many games. We're only going to play 3 because we've got a restricted amount of time here, a discrete amount of time. So I've got a score of 3. I'll continue. Thanks very much. My score is now 8. I'll continue again. My score is 9. That was a pretty lousy roll. My score is 12. I'll keep going. My score is 18. I think I'll sit on that one, so I won't play any further on the first game. And it says my score to date is 18. Game number 2, sucks to be me. The first result was a 2. I scored 0. I'm up to game number 3. The first score was a 5, so I'll go ahead and roll again. My second score was a 6. I'm looking good with 11. Oh, that was bad. I bombed out. And you'll notice what happens at the conclusion. It says you've played 3 games. Your game scores were 18, 0, and 0. The decision roll, that is, what was the score in each one, was 12, 0, and 11. So we can see immediately that in the first one, I made the decision, or I made the decision to keep on going, and I stopped at 12. When my score got to 12, I decided that's it. I'll do one more roll and I'm done. And then on the first one, my decision, I didn't even get to make a decision. It was a 2, and that was it. I bombed out. And in the third game, when the score got to 11, I decided to continue, and that was when my score was reset to 0. And how many rolls did it take? That's the third bit of data you get. That is, it took 5 rolls in the game in total to get to my score of 18. It took 1 roll to get to a score of 0, and it took 3 rolls to get to a score of 0. So there's some data that the students can use there to feed back some information. And ultimately, we're looking at coming up with a strategy. Do you decide to continue after a certain number of rolls, or do you decide to continue when your score gets to a certain value? Let me quickly show you what that looks like. Let's try Piggy 4. So this is set the target value. So I'll bank my score after 12. As mathematicians, you can decide whether that was a good choice or a bad choice. And it's simulating 100 games and collecting the scores. And it said your strategy was to bank the score at 12. Your average score was 6.98. And the results are scored in a variable called score. Quantity of rolls stored in rolls. So you can actually analyze both bits of information. Let me just drop in a data and statistics application. And let's have a look at score. So there's this really nasty column on the left. That's how many times I hit 0. And you can see there's nothing between 0 and 12 because I decided to continue playing for anything less than 12. There was a few games there where it stopped right on 12, and there's the distribution after it. So you can see I didn't get higher than 16 or 17 very often because I decide to stop at 12, so I can't get a score of 18. So that's what the distribution looks like. And then the students can perhaps score or look at what happens if I bank at 13 or 14 or 15 and so on. What does my distribution look like? And of course, the higher you decide to bank the score, the higher these zeros stack up. And then the students can start to make informed decisions based on the data they've got in front of them. So that's Greedy Pig. As you can see from that, it's a lot more sophisticated than let's just stand up and spend the last 5 minutes playing around. Another one I'm going to take a brief look at, and this might not seem like a probability question, but we're talking about randomness, so that is associated with probability. And what you're looking at, that picture on the left there, is not actually an ocean, it's a lake. It's actually the edge of the world's biggest freshwater lake, because arguably the biggest lake, I think, is the Caspian Sea. We can discuss that another time, whether that's a lake, but Lake Superior has an area of 82,000 square kilometres. Now, we could collect some what we call empirical data, that is, looking at the size of different lakes around the world, and I've done that for you. And I'm interested in the most significant digit here of the area of each lake. So with Lake Superior, we'd drop an 8 in as the most significant digit. The next biggest lake is 68,870 kilometres. That's pretty big. And then one at 59,000 and 58,000. So we've had a 6 and 2 5s. And now we've got a 3 sitting in amongst our distribution of significant digits. And then a 3 and a 2 and a 2 and a 1. And a couple more 1s. Looking sort of random. So my question is, if I start collecting empirical data, and if you're wondering what empirical data is, it's things like population. Or it might be, and this is getting a little bit closer to the core of what we're going to investigate, it might be, say, for example, the financial figures in your transaction column, in your bank statement for the last couple of years. And we'll just look at the most significant digit. So if someone can send me their bank statements for the last 10 years, that would be nice, and we'll have a little look through them. But otherwise, we're looking at how random are the digits 1 to 9 when we're looking at the first digit in any large data set. If anyone thinks they know the answer, they can drop that one in on the chat space, please. Turns out, a fellow by the name of Benford, he looked at it and said, here's what I got. He said, I think 1 occurs the most often. It's not random at all. Well, it follows some sort of a pattern at least, and it's certainly not an even or uniform distribution. That is, that the 1 occurs most often, then 2 and 3. Now, we're not going to do a whole session on Benford's law, although we could, but it's an interesting one to get students started because most students tick the box and say, I think the digits will appear uniformly. Unless, of course, we're talking about telephone numbers, because in Victoria, for example, they're all going to start with 9 if it's a landline. They're all going to start with 0 if it's a mobile. So that's kind of silly. We're looking at data sets, empirical data, where it's not forming some sort of a structure. And in fact, in 1991, the Taxation Office employed Benford's law to red flag people that were potentially cheating on their tax. Because the average person, if they're making up claims, will actually use random numbers. So they were able to align whether or not the claims that people were putting forward were indeed random or not. Now let me give you a quick example to help you understand how that might look. Let's suppose the biggest claim that you make, just like the biggest lake, was something of the order of $1,900 for a particular item. Then if you think about if the values were evenly distributed between 0 and 1,900, almost half of them would start with a 1 if they were randomly or uniformly distributed through that amount. That's a really quick analysis of Benford's law. You can have a look. There's plenty of videos out there on YouTube, but it's a great way to kick kids off with using probability to catch out fraud. And it's used, as I mentioned, in not just taxation, but also bank accounts to capture fraudulent transactions. Another one to look at is a news article. This one came up on the news only 2 weeks ago. There was a representative on the news from a lotto company talking about this multi-million lotto draw that was coming up. And to give you some idea, the advice that was given to the punters out there, if you like, is here's a list of all the numbers that have occurred most frequently. So we'll call those our lucky numbers. So if you want to increase your chances of winning, you should choose one of them. I kid you not, that was the advice, but it got better, or should I say worse. The next bit of advice was, oh, and here's the numbers that come up least often, and therefore we'll call them our unlucky numbers. In which case, I suggest you don't choose those to increase your chances of winning. And the final kicker, here's a list of the outlets that have had or sold the most winning tickets. So you should hurry off to those outlets to buy your next ticket. Now, I'm going to call that fake news. I know that's probably a bit political, but I'm going to call it fake news because I don't think the person in the lotto knew exactly what they're talking about. I don't think it was a news article. I think it was just a promotion. But it's either that the lotto company is trying to tell us that the lotto numbers aren't actually random and there's something physically wrong with their contraption that generates them, or for the mathematical types out there, perhaps you could listen to that advice and assuming that the average person out there will take it, then select the numbers that she said don't choose because you'll actually increase your expected return. Whilst they're just as likely to come up as any other set of numbers, the difference is, of course, you won't have to share it with as many people, although now I've announced that, that might stuff that up. You won't have to share your winnings with as many people as the average punter. But I think it's a good way to start a unit on probability because it gets students talking about the importance to understand probability and, in the case of Benfords law, not to look at things and assume randomness, that there may be patterns where you least expect it. It also means that students are focusing on some of the language that we use in probability. So let's have a look at some of the terms that we use. So, for example, variable. They're used to variable from algebra, I hope. So a variable can take on multiple different values. They get that. What about a random variable? That's actually a little bit harder for students to understand. A random variable can take on multiple different values, each occurring with some probability. And finally, for our discussion tonight, discrete random variable. Discrete random variable can take on a finite or countable quantity of different values, each occurring with some probability. So let's suppose x is our random variable, and we say it could take on the values from 1 through to 6. Each one occurs with some probability. Now I've just put the probabilities on the side there, p, 2p, 3p, whatever those values are. And if it's a probability distribution, or if we're talking about discrete probabilities, a probability mass function, then it has certain conditions that are required. You'll see also that the notation looks a bit like our functional notation. And if you think back, what we had was a mapping of x to probabilities, not that much different than how we have a mapping of x values to y values for a function. The notation that we use here, I'll go on the conditions first. I've got that the probability must be greater than 0. And also that the sum of the probabilities must equal 1. Now, some people will say, well, the probabilities have to be between 0 and 1, and that's what we usually give to students, but there's actually sufficient conditions provided there, because if all the probabilities are greater than 0 and they sum to 1, none of the probabilities can be bigger than 1. It's up to you whether or not you put that forward and get students to discuss it, or whether you just give them that they are between 0 and 1. Some of the notation that we use, capital X is for the random variable, and lowercase x is the values that our random variable can take. Now, we don't usually distinguish between capital and lowercase, although the student should have perhaps seen that in geometry, where they've seen angles for triangles or other shapes, where the angle is written as a capital letter and then the side lengths are written as lowercase letters. So they may have seen it before. Unfortunately, our calculator doesn't distinguish between an uppercase and lowercase letter. So here's our probability for each of our values x. So how else could we represent that? Well, we could represent it as a table. That's one way that you can set out the probabilities in your distribution. And if we use the information that were given before, that is that all of those probabilities need to sum to equal 1, then we can do some simple arithmetic. And we'll call this our probability mass function. Now, taking just the one thing there, that those probabilities will sum to 1, of course, in this particular case, it would be trivial to use the calculator, but I'm going to show you how you can use it, because sometimes the questions students are given, they might have 2 or 3 different variables in here for the probability of 6 or 4 or 2 or something like that. And they might give you information such as the mean of the distribution or the variance or standard deviation, and therefore have to work out each of the variables within the table. And therefore, students might appreciate the method that I'm about to show. So, I'm going to start up a new document, and I'm going to put a listing spreadsheet in. I'll give my X values a name. I'm going to call them XX, mainly because I don't encourage students to use X as the name of a list, because it can get confusing when you try and graph things. Now, I could use a formula to populate those values, but there's only 6 of them, so I've just typed them in. Now, for this, I'm going to write PR, short for probability, and I can put the values from the table. And let's see how well I can remember them. And this is something that our Nspire can do, at least the CAS version. And for those people that have joined us from Queensland, the CX2, which I'm using here, you can actually turn the CAS functionality off. So it's most likely going to be approved in your area, so you can see that that might be good. Of course, that means that they can't use it in the exam still, but they can use it during their learning. So I'm going to add in a calculator application. Now, I can do something sort of calculator-ish and say I'll get, say, for example, X times each of those probabilities. So we can do things like that. Or I can just write PR. I can add up all my probabilities like that. But what I do like is to use the sigma notation. So I could say X equals 1 to 6, and we'll sum up all of our probabilities. Now the notation here, I've got to use the square brackets because PR is a list of values, it's not a function. And that's why I'm using the square brackets. And you'll see there I get the same answer as I did up there. Again, so far it's trivial because we could have added them up in our head. But of course, and this would also be trivial, is to solve that equal to 1 P. Perhaps less trivial to grab this answer and say the sum of our probabilities is equal to 1. What does P represent? Same thing, of course. So now we have a value for P, we could then populate our table with the appropriate probabilities. Typically, we get questions like, what is the mean of this probability mass function? So we can see we've got X times the probability of X. So let's do that one. I'll go back and I'll grab my summation command and I'll just put in X times. And here's where it starts to get powerful. That would have been a little bit more work for students to do or arrive at 33p. So you can see if I had to solve it given some mean, I could now do that. Of course, I could also do it, say, given that P is equal to 1 on 10, which is what we calculated before. How does that look like in the table? Well, this is what we'd expect students to do. X times the probability of X, and then sum them up. Students still do that by hand, but as you can see from the next slide, what about things like the variance? Can we do that? We certainly can. If I go back here, I can put in an X squared here. Going to get rid of the temporary assignment of our probability. So I can get that one, and I could do that one minus, before I do that one, and let me just edit that a little bit. And then we have an expression for the variance. So if, for example, we were given some other values in here, let's say A and B, if I go back, I can then calculate an expression for the mean in terms of A, B, and P. So if I was given mean, I've now got one equation. I could sum up all the probabilities. And if I knew the variance as well, there's my expression, as ugly as it might be, for the variance with A, B, and P. So if I've been given those three, I've now got three equations, three unknowns, reasonably confident I could then go ahead and find out what the values of A, B, and P are. And of course, if we're doing it by hand, that's the sort of stuff we'd expect students to be doing. So hopefully you've seen various ways that we can use the spreadsheet, including putting variables in the spreadsheet to do some simple probability calculations. Now, if we get time, I'll show you how to make a list vary in length for a nice binomial distribution. But I'm also looking at the time, and I know that Peter Flynn is on the line here and wanting to do some work with dice. So I'm going to transfer my screen across to Peter. Are you there, Mr. Flynn?
I am. Lovely dissertation. Thank you, Peter. Can you see my screen?
We can indeed. It's all over to you.
Okay. So I feel as though that when we introduce discrete random variables to students, in the past we've probably tended to look at it from a theoretical perspective, and I feel as though that it's really important that we give opportunities for students to perform simulations, quite simple simulations. And so in that regard, we can fall back on the humble two six-sided dice distributions. And so I want to go through three of them with you this evening. One's the quite standard one there. If you have a look at my Word document, the sum of two six-sided dice, and of course we're talking about unbiased ones here. Now you've already gone through the importance of the notation, so it's critical that students understand that capital S represents a random variable, so we let random variable capital S represent the sum of rolling two six-sided dice, and the values that capital S can take are little s. And if we're talking about a six-sided, two six-sided dice, then S can take the values 2, 3, 4, etc. up to 12. Now, there are a number of ways that you can do this with students. You can discuss with them what the idea of a probability distribution is from them listing the outcomes using a tabular approach and then collating the results and putting them in the form of a table. You can also talk about the idea, as you mentioned, Peter, of a probability mass function, which describes a discrete probability distribution. And then we can also look at calculating various measures of centre in such a distribution. So we would need to talk with students about this notation capital E of S, the expected value or the mean of S, and we'd also get them to think about what might be the mode of S, you know, what might be the most popular sum in rolling two six-sided dice. So that one should be quite familiar to students. So, and the other thing here is I have an open mind about the order in which you introduce this concept to students. There is a school of thought to say to go theoretical considerations first and then experimental in the form of simulations, or to go the other way around. I don't think there's a definite right way there. I think if you do your job properly, then students should have a pretty good conceptual basis of what a discrete probability distribution is and what its properties are. So that's the bog standard one. The second one is a little less standard, but students may be aware of it, is rather than looking at the sum of rolling two six-sided dice, what you do is you look at the difference between the two six-sided dice. And so in that instance, it's nice to use a different letter and a letter that sort of rings a bell with the students. So if we're talking about difference, then we can say, well, let's let random variable capital D represent the absolute value of the difference of rolling two six-sided dice. A nice offshoot here is you get a chance to also talk about the idea of absolute value. You know, so the absolute value of 1 minus 3 is the absolute value of minus 2, which is 2, for example. So that's a nice offshoot. We could also get the students here to determine the probability distribution for random variable capital D. Can also be in the form of a table. Ask them to find the expected value of D and also to write down the mode of D. Another, I think, useful thing to do with students is before performing any calculations of expected values, it would be a nice idea to ask them to, once they've got a sense of the probability distribution, to ask for them for an estimate for the mean. I think that that would be a worthwhile discourse to have with the students. Now, we've gone from standard to not so standard to one probability distribution here that is quite non-standard but has a lovely algebraic generalisation. So in the third one, what we do is from the two six-sided dice, what we do is we just take the maximum result from the two dice. And so in this instance, we let random variables capital X1 and X2 represent the outcomes of the first and the second die roll respectively. And then we define a new discrete random variable capital M, so capital M standing for maximum, such that random variable capital M is the maximum of X1 or X2, the outcomes on either the first die or the second die. And we can get the students to determine the probability distribution for random variable capital M, and again, this can be in the form of a table. And again, we can ask them to estimate the value for the mean, the expected value, and we can also do a calculation. And we can also ask them to write down the mode, you know, what's the most frequent value of random variable capital M. So before we, I mean, in a few minutes' time, we'll have a look at how we can simulate this on TI-nspire technology. I just want to show you the first results in a way that you may not have expressed it before. So when you're discussing the sum experiment with the students, I think the best way to go about it is for the students to list the outcomes in a table and then tabulate the results. But you can also write it as a function with a really nice symmetry there. So I've got P of S. Now that can also be written as PR open bracket capital S equals little s. So I'm actually using unfamiliar notation here just to make you aware that there is alternative forms of notation here for probabilities. And so you can see there that for the extremities, the S taking the values 2 and 12, the probability, or P of S equals 1 on 36, and then that increases all the way up till you get to the figure that the students should have an intuition about, that the mode, or the most popular sum, we expect it to be 7. And that occurs for 6 outcomes out of a total of 36. And notice also that we've got the otherwise branch specified in that probability mass function. So for the 1 on 36, S can take the values 2, 12. For 2 on 36, it's 3, 11. So it's nice there that the first number's going up by 1, the second number's going down by 1, and you add the two numbers together and you get 14. I think it's what we need to do with students is to give them a chance to appreciate symmetry as well. I mean, symmetry is such an important part of mathematical thinking. With the probability distribution in a table, we can specify the formula for the expected value, So we can call it mu. So mu equals E of S, and that's the sum of each of the values that random variable capital S can take multiplied by the probability associated with it. And so what you do is you sum all those products, and lo and behold, you get 7. And the students should also have an appreciation that the mode of S is 7. So, you know, that's something that the students, I mean, we're talking about introducing this in year 11, but most likely in year 12. But students should have a good idea of this back in year 7 and 8, you know, with a good treatment of probability in the early years. The second one is a lovely distribution where we talk about random variable capital D representing the absolute value of the difference. And what you would do there is the students again would use a tabular approach. It's collated. I'm using the alternative unfamiliar notation here. And I've got this one specified in 2 forms, one in probability mass function form and also in tabular form. So in this instance, the probability that random variable capital D equals little d is 6 on 36 if D is 0 or 3. So, you know, so that indicates that you've got, for the 0 case, you've got 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. Then you've got 10 on 36 for D equals 1, 8 on 36 for D equals 2, etc. So you can see there that the mode is actually 1, the most popular, the most frequent value that random variable capital X can take is 1. And because the distribution is non-uniform and the probabilities peak, if you like, for 0, 1, 2, and then taper off for 3, 4, 5, it's like, well, where do you put the line that would indicate roughly where the mean of, what's the mean difference? What's the mean difference here? And it'd be really nice to get students to estimate it. If they look at it and they say, well, do you know what? Half the, you know, we've got a probability of getting D equals 1 or D equals 2 is 18 on 36, so that's half. And then it tails off. So you would expect to have a mean, you know, somewhere between 1 and 2, and probably between 1.5 and 2, actually, if you're doing a decent estimate. And we can then go on to do the theoretical calculation, and we can find there that the mean is the expected value of D. Again, what you do is you take each value for random variable capital D, multiply it by the probability associated with it, and then you sum the products. And what I would consider doing actually is, you can see there I've got 3 forms for the answer. It's nice to keep the unsimplified form actually, so I think I'd be promoting 70 on 36 as my answer. So in other words, keeping the probability distribution table, the respective probabilities, all as a denominator of 36. So I wouldn't bother doing the simplification, because sometimes the simplification can, you know, mask what's going on. You know, if that becomes 1 over 6 and that's 1 over 9 and that's 1 over 18, I think it's better if they're all specified in terms of the same denominator. And as we said before there, the mode is 1. So we'll get to the third one. I'll start with the third one, which is by far and away the most interesting. Then we'll have a look at the 3 of them from the point of view of TI-nspire technology and how to simulate the probability distributions, and then come back and look at a generalisation for this lovely distribution. So we've talked about how it's constructed, and you can start off a table with the students where you've got random values for random variable capital X1 down the left and for random variable capital X2 along the top. And each cell in the table gets the maximum of the 2 values. So what you see there is a partially completed table. And so what you'll see for 1, there's 1 possible outcome. For 2, there's 3 possible outcomes. For 3, there's 5 possible outcomes. And you get that lovely pattern developing. It's sort of like a reverse L. So for the case m equals 3, what you can see there is you can, well, to get for each of the values for random variable capital M, what you do is you just count up the entries that are 1, that are 2, that are 3, etc., up to 6. For example, when we look at M equals 3, random variable capital M equals 3, we've got 1, 3, 2, 3, 3, 1, 3, 2, 3, 3. So P of 3 is 5 on 36. And again, we tabulate the distribution and we get this lovely result. So we've got our possible values for random variable capital M, 1, 2, 3, 4, 5, 6. And you can ask the students, well, what do you notice about the respective probabilities? And they can say, well, they seem to be increasing, and they seem to be increasing at a constant amount. They seem to be, as you increase the value of M by 1, the probability is going up by 2 on 36. And it's a uniform increase, so it's a bit like a step function. So there is a lovely generalisation for that I'll hold fire upon. But what I want to do now is to give you an illustration of how to simulate these three distributions. So I'm using a TI-nspire file that I constructed recently. Now the first page that I'm going to talk about here, when you're using TI-nspire technology, what you need to do is you need to what's called seed the calculator. For example, students at the start of the year, they all take their calculator out of that shocking plastic container, and hopefully they haven't cut themselves. You get them all organised. Now what's going on with all those calculators is that they're all on the same factory setting. So the pseudo random features of the device are all set to the same thing. So if you don't seed the calculator and you do a simulation with the students, every single student in the class will get the same result. And what you've done is you've just destroyed their notion of randomness forever, and you've probably lost them as a teacher. In one of my first ever classes, I think in 1990, I may have done something quite similar. Once you do it once, you never forget. So what you do is you find the randseed command, which is under the random number commands, and what you do is, after pasting randseed onto your calculator page, just put in a phone number, your mobile phone number. It won't take the leading 0, so you don't worry about that. It would be a mistake if you chose, in a large class, be a mistake to use birthday, because there's a good chance that there'll be at least 2 students in the class sharing a birthday. So go with something like your phone number. So on that page, you would enter your phone number, press enter, and then what happens there is that your calculator is put to a different part of the pseudo random number generator, and it'll just go off into its own world, as do all the other calculators in the classroom, rather than them all being, giving out the same results. So to perform this simulation, this spreadsheet is the engine room. This is where it all happens. And with a little bit of explanation, I'm pretty confident that all of you should be able to make such a spreadsheet. Now, if you haven't used the list and spreadsheet application before, along the top, these cells are called column heading cells. And when you're analysing data in the list and spreadsheet environment, it's important that each column has a variable attached to it, so that you can use that variable for whatever purposes of calculation or transference of data or plotting statistical curves. So what I've done here is, in the column A heading cell, I've typed in die1 and pressed enter. It won't take a space, so don't try a space. If you wanted to separate the E and the 1, you can go underscore, and underscore is accessed by pressing Control and then the space key, but we won't worry about that too much. So what you can do is, you've got die1, die2 in column B heading cell, then the column C heading cell is the total. You can't use sum, so this spreadsheet is housing the 3 distributions, all right? So you can't use sum, that's a reserved name, so that's why I've used total, diff for difference, and then maximum for maximum, would you believe? So let's go back now to the column A, and then let's look in the cell underneath, which is the formula cell, and this is where you put the formula. So we're saying that we want die 1, and we want to access random integers from 1 to 6. This is a 6-sided die. So to get randint, what you would do is you would press menu, then 3 for data, 5 for random, and then you choose number 2 for integer. So that would paste randint into the formula cell. Have a look down at the entry line here. You don't see 1, 6, and so LV stands for the lowest value. So in this case, it's going to be 1. I'll show you where I've stored that in a moment. UV is the upper value on a 6-sided die, so that's 6, and N is the number of trials. So, I mean, when you're first making such a spreadsheet, if you had 1, 6, 100 and pressed enter, you'd get 100 results very, very quickly. I just want to toggle over. What I've done here in column F is I've used the assign command to assign N to be 100, so that's the number of trials. In cell F5, I've assigned LV to be 1, so that's the lowest value on a 6-sided die. And then I've assigned UV to be 6, which is the largest or maximum value on a 6-sided die. Notice they come up, they're bold. They're bold because they've been assigned. So that assign command is colon equals, and colon equals, you can see on your keypad, is accessed by pressing Control and then the symbols template. So you can hopefully get a sense of, we can control the number of trials, and we can also control the number of sides that the 2 dice have, which is quite nice. So we go to the formula cell for column B, and it's basically a repeat of what we entered there in column A. And what happens is when you press enter, the column populates, in this instance, with 100 results. We go to column C, so this is for the probability distribution where we're looking at the sum. And it's nice because you ask the students, well, okay, what formula should we put in? And the formula is die 1 plus die 2. These variables are housed inside the variable command. So if you press variable, what will come up is a list of all the variables that have been assigned, and rather than typing them out, you can just select them from a pop-down menu, which is really useful. And interesting there, we now go to the difference, and the difference is the absolute value of die 1 minus die 2. You might notice that in these formulas you've got these little like exclamation marks there. That's denoting that die 1 is actually a variable, so that's nice that you see that. So again, ask the students, well, okay, what formula should we put in here, rather than just telling them, and hopefully they can formulate the right formula and put it in there. And if you have a look here, it's quite simple here for the maximum. It's just the max of die 1 and die 2. Where do you find maximum? What you would do is you'd press menu, then number 3 for data, and then number 6 for list math, and then number 2 is maximum. So basically what we've got here is we've got 2 columns representing the 2 6-sided dice. We're throwing them 100 times, and we're getting the sum of the results, the absolute value, the difference of the results, and the maximum of the results. So you can see there. Okay, so let's have a look now at some calculations. Here we've got the this is the experimental mean, and so it's you would expect it to jump around 7, and it's coming out here for 7.13 for the approximate sum, the approximate mean for the sum of 2 dice. For the difference, it's coming out at 1.65, and remember we calculated that as I think it was 70 on 36 or 35 on 18, and we haven't gone through the mean for the maximum yet, but I can tell you that it's for the 6-sided situation, it is around about 4.5, so that's quite close. Now, what you could do is you could change the values for LV, UV, and N in the spreadsheet but what might be an even better idea for the visual learners is to set it up in a data and statistics page. So what you see there is a histogram with the permitted values or the allowed values of capital S going from little s going from 2 all the way up to 12. You can see that there's a vertical line which represents the experimental mean, which comes out, close to 7. And you've also got these sliders here. So at the moment we've got 100 trials, and at the moment we've got an upper value of 6. And so I would advocate not using n to be very large at all at the start. If you do, you'll kill the activity, because students will think that 7 will be the most frequent value no matter what. Here what you'll see is you've got a bimodal distribution where 6 and 8 are the two modes. And so I think it's really important to show students what happens for small values of n. This shows true randomness. If you started off with n equals 2,500, there's a very, very large chance that 7 is going to be the most frequent, and students don't get a chance to see the fluctuations. But what we can do is we can increase the number of trials, and we can see how this histogram behaves as we increase it. We can ask the students, what might you expect to see? And, really nice answers like, well, expect it to become more symmetrical. We're expecting 7 to be becoming a more and more prominent peak. So here we go. Now notice there at 300, it's 6 was almost the most popular over 7. And 6 is the most popular at 400. So you've got these random fluctuations taking place. Finally, when you get to 700, it's a situation there that's gone off the scale a little bit, where 7 ends up being the most frequent. So we take it back to 100, and we can do the same for the dice difference situation, and we can increase the number of trials there. And what you want the students to see is, as you increase the value of n, hopefully what we're seeing is that the simulation gets closer and closer to the theoretical considerations. And that's why I said it doesn't matter in what order you do the experimentation or the theoretical considerations. So bring that back to 100. And then we can also look at the third one here, which is the maximum. It's already looking a bit like a step function, and then we can increase the value of n, and it's becoming more pronounced. Nice. Yeah. So we're expecting to see a constant difference. There's still random fluctuations going on. You can also change the window, and that's going to be important when you change the number of sides on the die. So to change a window, what you do is you press menu and then number 5 for window zoom, and then number 2 for zoom data. So that's a really important way of changing the window. So what we might do is go back to one of these. Actually, we might just stick with the maximum one here, and you can change the clicker so UV becomes 4 all of a sudden. Okay, so now we've got a 4-sided die, and we can look at the probability distribution for a 4-sided die and increase the number of trials. And what you see there, again, we get this lovely step function, and we're expecting the increase in probabilities throughout to be approximately constant. And of course, through random fluctuations, that won't quite be so. Now, to finish off, so you can to finish off, you can change on your data and statistics page or your spreadsheet page. You can change n, you can change LV, you can change UV. But what I want to do is offer a theoretical consideration at the end for this third probability distribution. And we can ask the students, well, what about coming up with a general formula for the probability distribution? And for the 6-sided die, so where little m can take the values from 1 through to 6, we can formulate that P of m is equal to 2m minus 1 all over 36. And then what we can do is we can calculate the mean. The mean in this situation, as we've discussed, ends up being close to 4.5, and the mode of M is 6. Makes sense, because when you're going back looking at that table, your reverse sort of L shape gets bigger and bigger and bigger, covering more values. Now, to finish off, I've got a lovely algebraic generalisation where we now consider two R-sided dice, where M takes the values from 1, 2 all the way up to R. Now, I've chosen R to be 4, 6, 8, 12 and 20 to line up with the 5 platonic solids, so tetrahedron, the cube, the octahedron, dodecahedron and the icosahedron. If we calculate the mean, what we can do is we can come up with a lovely formula. Now, back at the formula where we knew what the denominator was 36. 36 is 6 squared. So this is for R equals 6. So we've got a constant here that we can take out of our summation expression. So we can say that mu is the sum from M equals 1 to R of M times P of M. And because we know that the 1 on R squared is constant, we can take that outside. And so we get 1 on R squared by the sum of, from M equals 1 to R, of M times P of M. Now, we've taken into account the R squared. It's M times 2M minus 1, so that gives you 2M squared minus M. Then what you do is, using summation properties, they can be split into the difference of two sums, with 1 on R squared taken out as a common factor. So the sum from M equals 1 to R of 2M squared minus the sum from M equals 1 to R of M. Some students may know these results. I mean, you can derive these results, but you can go straight to the CAS actually. And so these screenshots suggest what you get for the sum of M equals 1 to R of 2M squared. You get R by R plus 1 by 2R plus 1 all over 3. Now remember, R is the number of sides of the die. So from that, you subtract R by R plus 1 on 2. So it's the difference of those two, and you multiply all that by 1 on R squared. So the CAS is looking after the details. What you do and what the students do is formulate the results, and then the CAS looks after the algebraic details. And what you end up with through the CAS's auto simplification feature is you end up with a lovely result of the product of R plus 1 and 4R minus 1 in the numerator, and then 6R in the denominator. And what I've done in this screenshot here is I've substituted R equals 6 in there, and that confirms the result that we got for the 6-sided die back before the generalisation. That's roughly 4.5. And what you can also do is, for those 5 platonic solids, you can substitute the values of R, 4, 6, 8, 12 and 20 in the form of a list. And what these are your expected maximums for each of the dice, each of the situations. So for the 4-sided die, E of M is 25 on 8. For the 6-sided die, E of M is 161 on 36, etc., etc. You can also press Control Enter, and that will give you an approximate value. And the final thing is, just back at this spreadsheet, when I was looking at calculating these means, I don't know if I mentioned it or not, but I'm using the approximate command. So you can just type in approx, and what that does is it gives you a decimal representation for those experimental means, which is far more meaningful than the exact values. So that would be my way of looking at introducing discrete random variables, a mixture of theoretical considerations and also exploiting the power of TI-nspire technology to perform the relevant simulations. So I think that's about it from me, Peter. The cricket's about to start.
Okay, thanks, Mr. Flynn. I'll just grab back the screen. Very nice presentation, as usual. Just while we're waiting for that screen to drop over across to mine, it's having a little hissy fit at the moment. There it goes. Just a quick reference back to something that we or I put out at the very, very start of the webinar, was a question about tossing coins, because I like the ones that end up a little bit unusual. I threw out a question to people about if Alex and Gustav were playing a game where they're just simply tossing a single coin, and Alex wins if it's head, head, tail. This is a sequence. So in other words, you don't just win on head and you don't just win on tail. You specify a sequence, and the boys keep on flipping the coin until such time as their sequence comes up. So you can see there, that's the sequence of coin tosses. So eventually we've got a head, head, tail. And we'll run it again. There's another head, head, tail sequence. Alex has won 3 out of 3. Alex has won 4 out of 4, 5 out of 5, 6 out of 6, 7 out of 7. Clearly the game is unfair, although we haven't played enough yet. But eventually we'll get a Gustav. There we go, Gustav won. There was Gustav's option, which was head, tail, head. And at the moment you're thinking, well, that's not really enough samples. So the students can then go on and try it and say, well, let's take on a few more games and let's try for 25 games. Alex wins 15, Gustav won 10. And of course, we can look at whether or not that would be accepted, and that's reasonable to accept that at 95% confidence interval, assuming that the thing is fair. But let's see what happens if we play 50 games. Yeah, looking a bit dodgy. Let's play 100 games. I think most people would say there is something weird going on here because we've played a lot of games and Alex seems to be winning a lot more than Gustav. So indeed, the game is not fair. It's referred to as Penny's problem. I'll leave that one for punters to try. But now past our final time. So for those people that have joined us for the first time, your feedback is important. Even if you haven't joined us for the first time, you can give us some feedback. We certainly take it seriously. You'll receive a follow-up email within 48 hours of the conclusion of this webinar, which will include some additional links to a webinar certificate. And of course, this video will be available on YouTube very soon, where you'll find all of our past webinars and also a new series on specialist maths for students. We've already got some further maths and methods videos up for students to use their calculators efficiently in exams. Check out our website. And finally, if you haven't done so already, make sure you subscribe to our e-newsletter. We've got some workshops coming up in a couple of states, and you'll need to make sure you're in on those quick because those events chop up pretty quick. If you have any other follow-up questions, be sure to give us a call. There's a number. I don't think I saw any New Zealand visitors on here this evening, just Aussies and a couple of other overseas. I think I saw one from Singapore there. And another one from, I'm not sure where because I didn't see the original detail, but certainly not in Australia. And that's all for tonight's webinar. Thank you, Mr. Flynn, for joining us.
Yes, thank you very much. Well done.
And that's all. Yes. Thank you very much. And thanks, everyone, for joining us. And be sure to catch us on our next webinar. That's all for this evening. Bye.
Good night.